Okay, before we move on to Q calculations, there's one other time where we can calculate equilibrium concentrations of ions. And this is something where we have a common ion and something called the common ion effect. This is the definition of the common ion effect. So, an ionic compound's solubility is lowered when you have a common ion present in the solution. So what that means is, if I have, well, let's say copper bromide, and I want to figure out how much of it will dissolve in water. Well, if X amount dissolves in pure water, then some number smaller than X amount will dissolve in a solution that already has either copper 1 ions or bromide ions. So I can make a solution from pure water, or I can make a solution from something that's already a solution. And this happens again when you look at water quality and water quality testing, and we're looking at concentration of ions that occur in very small amounts. So what does this look like? Okay, this question: calculate the solubility of CaF2, calcium fluoride, in a 0.025 molar sodium fluoride solution. Well, I do have my Ksp value given, so I should be able to do this. First thing, equation. Second thing, Ksp expression. Okay, next, I set up my ice table. Again, X to remind me that nothing goes there. So now when I read this problem, before when we were calculating the solubility, there was nothing. We had pure water, so there were no ions there. But right now we have a solution of sodium fluoride, which means there are already some fluoride ions there. So there aren't any calcium ions, but I have a concentration of 0.025 molar fluoride ions, because there's one fluoride ion in this formula. So my initial concentration, instead of being 0, is 0.025. Now, since there isn't any calcium ion, I do have to shift to the right and have some more has to dissolve to get to equilibrium. And if the amount of calcium is X, then the amount of fluoride is going to be 2X. And when I get to equilibrium, that concentration will be X, but this concentration will be 0.025 plus 2X. So because I already have some fluoride in solution. Now when I come to plug this in, I see 4.0 times 10 to the negative 11th is equal to the concentration of calcium times the concentration of fluoride squared. Now the first thing you'll notice is that this is going to be nasty. This is going to be a nasty quadratic cubic equation. So there must be some way to simplify this so we don't have to do all that math. Well, as it turns out, there is. The solubility of calcium fluoride is pretty small to begin with, and since it's going to be even smaller because we already have fluoride solution in here, we can estimate the value of X and solve this by ignoring this 2X, because once I figure out what X is, we're going to see that that value is so much smaller than 0.025 that when we add it to 0.025 and round to the correct number of significant figures, that number will stay 0.025. So if I pull out the 2X, this becomes a much easier equation to solve. And in fact, X equals 6.4 times 10 to the negative 8th, and that's equal to the concentration of calcium ion, and since there's one calcium ion in calcium fluoride, it is also the solubility of CaF2 in moles per liter. Okay, because if we evaluate this x, that's 10 to the negative 8th. So if I take that 0.025 and plug in twice that, which would be actually 1.28 times 10 to the negative 7th. One, two, three, four. Okay, got my number of zeros right. I get 0.025000128. So really, that x, even though it's going to be slightly larger than that, is not going to be large enough to affect this 0.025. So I can safely ignore x in the the 2x in the 0.025 plus 2x that appears in this equation. Okay. Now let's look at Q. Okay, again, Q, I don't know if I'm at equilibrium, and I compare the Q value to Ksp. Well, let's think about this. Remember, for the general Ksp expression, we have the concentration of A plus to the x times the concentration of B minus to the y, given this equation. Okay, so I can calculate a Q. Remember, the Q expression looks just like this, except that I'm not at equilibrium. So, not at equilibrium, at equilibrium. Okay, so now if Q is greater than K, so my actual concentrations are greater than the K value, then that means I have concentrations that are above the saturation point, above the molar solubility, so you should get precipitation. If Q is less than K, then that means these concentrations are not high enough to be at equilibrium yet, so you cannot get precipitation. And then if Q equals K, then I have a saturated solution, but with no solid on the bottom. So let's take a look at one of these problems. So we're mixing two solutions together, a nitrate and an iodate solution together. Now you notice in both cases this iodate solution right here. So this nitrate solution and this iodate solution. I want to know if cerium iodate will precipitate. So the first thing I want to do is, since I'm asking whether that will precipitate, that is the equation that I'm worried about. The K for that, Ksp, is equal to the concentration of Ce3 plus times the concentration of IO3 minus cubed. Okay, the next thing I have to do is calculate the actual concentration of each of these ions in this solution. Because what I'm doing is taking 750 milliliters of one solution and adding it to 300 milliliters of another solution. So the total volume, when I put those together, is 1.050 liters. Okay, which means that the concentration of each ion has now changed, because I have the same number of moles of cerium and iodate, but now they're in a different volume. Instead of the cerium being in 750 milliliters, it's in 1.05 liters. Instead of the iodate being in 300 milliliters, it's in 1.05 liters. So to calculate the new volume, I need to figure out how many moles of each ion I started with. So for cerium, I started with 0.750 liters of a solution that was 4 times 10 to the negative third moles per liter, and that's equal to 3.00 times 10 to the negative third moles of Ce3 plus. Now this number of moles is now in 1.05 liters, so the new concentration is 2.86 times 10 to the negative third molar. That's for cerium. For my iodate, I started with 300 milliliters of a 2 times 10 to the negative second mole per liter of solution, and that's 6 times 10 to the negative fourth moles of iodate, and that is now in 1.050 liters. So that tells me that the concentration of that ion is 5.71 times 10 to the negative fourth molar. So these are the concentrations that I put in my Q expression. Because remember, the question is, will a precipitate form? Which means, is the system at equilibrium? Which means, solve for Q. So now, I plug the numbers in. There is my cerium. There is my iodate. And that is equal to 5.32 times 10 to the negative 13th. Okay. That's Q. K is 1.9 times 10 to the negative 10th. Q is less than K, so no precipitate. And that's how I predict whether or not a precipitate will form.